am Lord Sen from National Institute of Technology, Rourkela, and today I will be presenting our work on mapping networks, carried out jointly with Professor Syamapada Mukherjee. Deep learning models today are becoming increasingly large, often containing millions or even billions of parameters. While these large parameter spaces improve expressivity, but they also introduce several challenges like high memory requirements, longer training times, complex optimization landscapes, and severe overfitting. Our work is motivated by the observation that the training trajectories of large networks lie on effectively smooth low dimensional manifolds as shown in these two plots. Based on this idea, we propose mapping networks, where instead of directly training all the parameters of a large neural network, we train a smaller latent representation and map it to the full parameter space. We begin with a small latent vector. This latent vector is passed through the fixed orthogonally initialized mapping weights, which generates the parameter space, and these parameters are then used for feed forward and inference. So rather than optimizing the millions of parameters directly, we are now optimizing a structured low dimensional representation that captures the essential geometry of the parameter manifold. This framework has several advantages. First is significant reduction in trainable parameters, lower overfitting, faster training, and improved parameter efficiency. Furthermore, we can combine this mapping network with techniques like low rank decomposition, pruning, and quantization to further make the approach more efficient and decrease the inference time also. An important contribution of our work is the mapping theorem, which provides a theoretical justification showing the existence of a mapping function g from this low dimensional latent space to the high dimensional parameter space. The practical achievability of that mapping g is shown by the second theorem. The mapping function is for the fixed orthogonally initialized mapping weights, which are modulated using the latent vector by a additive modulation. To fine-tune large networks, we can use mapping networks to generate a tuning vector, and this tuning vector will tune the pre-trained parameters which will be used for the feed forward and inference. To ensure that the learned manifold remains smooth and stable, we introduce a mapping loss consisting of 4 components. First one is the task loss, which ensures good downstream task performance. Second is the stability loss, which penalizes the output changes, large output changes due to small perturbations. The smoothness loss, where we regularize the Jacobian norm to preserve the differentiability and smoothness of the manifold. And finally, the alignment loss, which improves the compatibility between the latent vector and the mapping weights. We further explore 2 different training methods. First one is SLVT, where a single latent vector approximates all the parameters of the network. This works well for smaller networks, but as the model grows in size, the number of fixed mapping weights grows significantly, increasing the memory requirements. Hence, we adopt layer-wise training. Here, instead of one latent vector, we assign in different latent vectors to individual layers, which is supported by the observation that the training trajectories of different layers lie in different manifolds. This not only reduces the memory requirement but also improves the scalability of our approach. We have evaluated our model across different datasets and tasks like image classification, defect detection, and image segmentation. We have observed that for FashionMNest dataset, while training, we got a training accuracy of around 99.10%, but the test accuracy decreased to 92%. So there is a huge train test gap. But while training using mapping networks, the train test gap was just 1.8%. Furthermore, for tasks like image classification, where only a certain part of the image is important, mapping networks tend to give comparable or better performance. But tasks like image segmentation, where the entire image is important, the normal training performs better. Thank you.